Hello, everyone, and welcome to another episode of Mechanical Drawing 202. In this episode, we will be introduced to lines in space. Alright, so normally, when drawing in technical drawing, a lot of our lines tend to be either vertical or horizontal. Now, if you observe these two objects, you'll realize that they consist of vertical lines and horizontal lines. All right, so that may sound confusing because you're seeing some sloped lines. Now, in the isometric drawing, as we all know, we recede lines at 30 degrees, right? But these receding lines here, they are representing horizontal lines, while these that I'm clicking on now, they represent vertical lines. They are being displayed as vertical. Now, that is the fact. This is so because isometric projection is skewing the angle of the line so as to give a realistic look or give the type of look, the realistic pictorial look. Now, let's look at the orthographic views for these objects. If you realize, even though these lines are sloping, the orthographic views are showing that these lines are indeed vertical and horizontal. Let me move up. All right, so these objects are drawn in a particular space, and these objects are consisting of lines. All right, they consist of lines. All right, so this line that was once seemed inclined, it is actually straight. So it's actually a horizontal line. This line is actually this line. This line is actually this line. This is the plan view. This is the plan view here. This is the edge of the plan view. This is the edge of the plan view. So if you realize with these two objects, all the lines either fall on the vertical axis or the horizontal axis. Or if you're looking at it from a 3D perspective, x-axis, y-axis, and z-axis. So the x-axis is horizontal, the y-axis is vertical, and the z-axis is also horizontal in terms of the direction of measure. All right, so for the planes, it's different. Let me explain that further. All right, so let me explain that further down. All right, so let's look at some objects, like for example, this one. If you realize this line is inclined, this line is also inclined. So these lines, if you look on the front view, you'll realize that they are inclined. It's inclined. All right? However, on the plan view, it would be, give me a moment, this line. And it is being reflected as a vertical line because you're looking at it from a bird's eye view. So it seems to be straight or not inclined. It seems to be parallel to the horizontal plane, which it is not. Over here, it's the same thing. This line here is representing this line, which is representing this line. But if you realize these lines are not the same measurement as this line. But if you look over here, this line is this line, and they are both showing the same measurement. And you notice it's not being shown over here. It's due to the fact that these lines are corresponding or parallel to one of the planes. They are either vertical or horizontal. So look here. Look again. This line represents this line, but you're not seeing it over here. This line is a horizontal line. When you look at the object in a 3D perspective, it's right here. So It's parallel to one axis and it's perpendicular to another. This means that the true length of this line is being shown here as well as here. It is reflected on multiple views, similar to this line and this line. The true length of this portion here can be seen. Once the line is vertical and horizontal, the true length of that line can be seen on any view. Alright, this might seem like it's taking a little while, but bear with me. I have to explain all of these things so that when I get to the meat of the matter, you understand clearly what I'm saying. Now let's go back to this portion. This line and this line, they are reflecting two different measurements. That's due to the fact that the line is an inclined line, right? So in a situation like this, we have to know which one of the views the true length of that line is being reflected on. All right, so this is the line that is in question. Normally, the view that the line appears the longest will be the true length. That is the front view. Another thing that you can use to determine the true length is observe the view that the line is sloped in. Now the line is appearing as a horizontal line here. It is appearing as a vertical line here. So we definitely know, since it's an inclined line or a line that is sloping at a particular gradient, we know for a fact that these are not the true lengths of the line. This is indeed the true length of the line. All right. So far, so good. So whether a line is straight, meaning vertical or horizontal, or whether it is inclined at an angle, we can determine the true length of the line depending on the situation. However, if you notice here, this line, it is inclined on one plane but straight on another. Let me give you an example. Look at this line. This is the line that is existing in space. However, it is sloped. All right. If you notice, this is a bird's eye view of the line. This line here. This is a bird's eye view of the line. Right? So if you look, you'll realize, looking down on the line, you're seeing the line at a particular length. If you look on the front view of the line, you'll also realize that the line appears shorter. Why? This line is at an angle to this line. Right? This line appears shorter than this line. This is the side view of the line now. It appears shorter due to the fact that this line is not parallel to this line, to the plane. So the vertical plane that is responsible for the side view, this line is not parallel to it. That is why it appears shorter. And it is appearing now horizontal. It's appearing horizontal here. It is appearing at an angle here. And if you notice, this length looks like this length. Right? So in this example, this would be the true length of this line, while the other views are not showing the true length. And if you notice, the lines are horizontal here. All right, let's go back to this drawing. If you notice this line, it is appearing as a true length in one view, while not appearing as a true length in other views. So this, let me show you another example of this. Or before showing you the example of this, let me show you how this line would appear if we're supposed to draw it in orthographic projection, meaning showing the different views. All right, so this is the plan view. And if you notice, this is it. Line AB, plan view. Line AB, front view. Right here. And this is the side view. If you notice, this line represents the true length of the line. These lines are shorter. This line is longer. And as such, it is representing the true length. When looking at a line at an angle, the line either appears as its true length or appears shorter. It will never appear longer. Right? So this is the true length of this line that you're seeing here in space. And in this situation, the true length is being reflected on the plan view. In this situation, the true length is being reflected on the front view. Now let's look at another example. This is another line in space, and this time, this line is parallel to a line on a vertical plane rather than on a horizontal plane. So this line appears shorter than this. This line appears shorter than this. Let's look at the different views of that line. If you notice, on this view, the side view, it is appearing as the true length. And the other views, the lines are appearing straight. If you notice, in this situation, the lines appear vertical. They are not the true length. These lines appear horizontal. The sloped line, once a line slopes, it tends to be parallel to one axis. And once it is parallel to one axis, on that view, you can get the true length. Right? It is not parallel to this because it's sloping. It is also not parallel to this because it is sloping. Right? And you can determine the angle of the slope. Right here, you can see, if you measure here, this is an angle here. All right, so since I'm measuring in isometric projection, this angle, the measurement that you're seeing will not be correct. So this is showing 21. It's not necessarily 21, the slope. All right, so this is showing a slope. And this line, the angle between these lines would be the same. Right? So that is the slope. But if you notice, these lines are parallel. Right? So you will not get an angle between them. All right. So for these two examples that I've shown, the line is parallel to at least one plane. It is parallel to one plane. So the plane that it is parallel to will show you the true length. So this is parallel to this plane. This is parallel to this plane. So you can easily look at the object to determine the true length. Let's look at this line now. If you observe this line, you will realize that this line is not parallel to any plane. It's not parallel to this line. This is showing the plan view of the line. It's not parallel. This is showing the front view of the line. It's not parallel. This is showing you the plan view. Let me show you why I know that it's not parallel. This line and this line is the same distance. So from this surface, this line, A is the same distance. The distance between the A points and the B points are the same. For this one, the distance between A and A here is the same, and B and B here. So this line, no matter how far you extend this line, it will not touch this plane if this plane was extended. The same principle applies here. This line is parallel to this line, so it doesn't matter how much you extend that line, this plane, it will not touch, even if you extend the plane. Here, this line is neither parallel to any of the planes. Let me show you an object that consists of a line, like what I'm describing here. This line is parallel to at least one of the planes, whether horizontal or vertical. This line is the same. This line is not parallel to any plane. So when you're showing the views, you will not see the true length of this line, because this line is not sloping in one direction. It is sloping in. It is sloping. All right. Let me see if I can say this in the simplest way. This line. Let me use this one for example. This line is sloping in this direction, but it appears straight here and it appears straight here. Now this line over here, the one that we're examining now, it does not slope in only one direction. So it's sloping this direction, but it is also sloping backwards. So if you look on the plan view, you realize that it's sloping backwards, right? So it's sloping two ways. And when you find an object that consists of a line that is as such, you will never see the true length of the line on either of the views, right? So this line is not the true length. This line is not the true length. This line is not the true length. So the true length now has to be calculated, right? So you cannot just look on the object and determine that, oh yes, this is the true length, because it is only sloping on this side. You have to now graphically determine the true length of this line. And you can determine the true length of this line if you are aware of the slope. Hold on, never mind. You could have determined the true length of this line based on the slope. All right. Once you create a line that is perpendicular to the slope, you will be looking on the true length. What I should have said is that you can create a view that is showing the true length other than this view. And that view is neither a front view or a side view or a plan view. We refer to that view as an auxiliary view. Now with this drawing, you can also draw an auxiliary view that can show the true length, but it will be very difficult. Now we can graphically determine the true length of this line if we isolate this line. Right, we can isolate this line and show the true length. So if you look at this line right here, this is the line that one of the lines that I was talking about. It does not reflect the true length on either vertical planes or horizontal plane, right? And as such, you will see it being reflected like this. So none of the views are showing this line as a straight line. In none of the views, the lines are parallel or perpendicular to our axis. These parallel to the vertical axis, these parallel to the horizontal axis. So in a case like this, you have to graphically determine the true length as well as the true slope of the line, right? None of these views are showing the true slope of the line either. While for these, you can instantaneously see the true slope. This angle theta, whatever this angle is the true slope of this line to the axis, this axis here. And this is the true slope of this, right? So this line in space, let me show you something. It slopes 30 degrees to the horizontal axis, right? So it's on the vertical plane. It's sloping 30 or whatever degrees it is. I shouldn't have said 30. It's sloping a particular degree to the horizontal axis. Over here, this line, it's on the horizontal axis as the true length. It is sloping this angle to the vertical axis. So this is the vertical axis and this is the angle right here. So this line is sloping whatever degrees to, let me specify the angle. So this angle here is 31 degrees. So that angle, this angle is 31 degrees. So this line is sloping 31 degrees to this axis, and the true length is reflected here. This line is sloping 20 degrees to the horizontal axis, as you can see here. And this is the true length. Right? So while it's on the vertical axis, it's being shown on the vertical axis, the slope is sloping. This is the angle that it slopes to the horizontal axis, while this one is being shown on the horizontal axis, but this slope is to the vertical axis, as you can see in this illustration here, the line in space. Now, over here, this line is not parallel to any of the axes, and in none of these views can you determine the true length. In none of these views can you determine the angle that it is sloping to whatever axis. So we don't know the angle that it is sloping to this axis, or this axis, or this axis, because the line is not parallel to any of these planes, vertical planes or horizontal planes, any of these axes. So in a situation like that, as I said before, we have to determine we have to use the graphical means, or we can either use calculations as well, but in this case we are going to use graphical means. So in future videos I will show you how to use the graphical method or a graphical method to find the true length and the true slope of a line that is not parallel to either axis, right? And there are multiple methods that can be used, and in the next video we will go through those methods. Further videos in this series will go through those methods. I hope this video was informative. I hope you grasped the concepts that was being taught in this video. If you have a question, please leave it in the comments. Please remember to share, like, and subscribe for more content. Have a good day.